Okay, so this is now for November 29, Thursday, November 29. This is week 14, day 2, a lecture on fluid dynamics. I will tell you a little bit about density and pressure, the hydrostatic equilibrium, the Pascal principle, Archimedes principle, and buoyancy, and then go actually beyond that, what really entails the dynamical part of fluids, namely the so-called Bernoulli equation. So let me first give you a little bit of background and define what do I mean with a fluid. As you all know from your chemistry, from your high school education, there are three common phases of matter. There are solids, there are liquid, and there are gases. A solid has a definite shape and size. Concerning these qualifiers, shape and size, a liquid has a fixed volume but can have any shape and conforms to a certain given boundary. And a gas can be any shape and also can be easily compressed, so it does not have a fixed volume. That's very different than a liquid. A liquid cannot be compressed. Liquids and gases both flow and are called fluids. A fluid, in contrast to a solid, is a substance that can flow, and fluids conform to the boundaries of any container in which we put them in. That holds for both a liquid and a gas, and once again, liquid has a definite volume, whereas a gas does not have a definite volume. And they do so because a fluid cannot sustain a force that is tangential to its surface. That is, a fluid is a substance that flows because it cannot withstand a shearing stress. It can, however, exert a force in the direction perpendicular to its surface, namely under conforming boundaries of a container, for example. And this is precisely what I want to address now, namely this new term of pressure. But first, let's start with reminding you the term of density with regard to a fluid. To find the density of a fluid at any point, we isolate a small volume element, V, around that point and measure the mass m of that fluid container within that element. If the fluid has a uniform density, then you can take any volume and take the respective mass and form the ratio delta m over delta V. That has to be, of course, the same as the total mass divided by the total volume. That is what we refer to as density. In the SI units, mass measured in kilogram, volume measured in cubic meter is therefore kilogram per cubic meter. So now the new term of pressure divides out to become independent of a certain area. So now imagine you have the cylindrical container with a liquid inside, for example, water. That liquid exerts pressure perpendicular to a certain conforming surface, for example, this little cube here inside, so perpendicular to that surface. So what you now do to become independent of that particular area here, you take the force exerted onto that area and divide it by the area. The respective area, and that particular ratio is called Pascal. So force, as you know, is measured in units of Newton, area in units of meter square, and that ratio 1 Newton per meter square is called Pascal. And as you know, there are different types of pressure units around which you have, I'm sure, have heard. For example, if you put air in your tire, you hear about a PSI. For example, my car, I'm driving a Volvo station wagon. There you have typically 36 psi. So now how does that relate to the SI unit of pressure, Newton per square meter, which is 1 Pascal? So 1 atmosphere pressure related to the air pressure is 1.01 times 10 to the 5 Pascal. That refers to 760 torr, or 14.7 pounds per square inch. And that refers to the unit of psi. I'll come back to that a little bit later. Pressure is the same in every direction in a fluid at a given depth. If it were not, the fluid would flow. Also, for a fluid at rest, there is no component of force parallel to any solid surface. Once again, if there were, the fluid would in fact flow. So let me give you a little bit of a feel for pressure. If we are talking about new quantities, it's you have to first get a feel for it. How large is 1 Pascal? So 1 Newton per square meter. So an automobile tire has typically 2 times 10 to the 5 Pascal Newton per square meter. Atmosphere pressure at sea level is typically 1. So air pressure is twice as large. The best laboratory vacuum is 10 to minus 12 Pascal. So let's go to significantly larger pressures. The spike heels on a dance floor. So if you take force and divide it over an extremely small area, then the pressure becomes very large, typically 10 to the 6. Deepest ocean pressure, it's typically 1.1 times 10 to the 8. We'll come back to that. The highest sustained laboratory pressure is about 1.5 times 10 to the 10. And the center of the sun is 2 times 10 to the 16, whereas the center of the earth is about 4 times 10 to the 11 Pascal. Always compare this with something that you know from everyday life. Atmosphere pressure is about 1 times 10 to the 5. Air pressure is typically twice as large. So now, in the presence of gravity, the pressure in a static fluid must increase with depth. This allows the upward pressure force to balance the downward gravitational force. This condition is called hydrostatic equilibrium. Details depend on the nature of the fluid. Incompressible fluids like a liquid have a constant density. For them, the pressure as a function of depth is. So, meaning pressure linear increases with depth here. So the pressure here at the bottom is much larger than here on the top here. And the pressure would be the pressure at that surface here. So the pressure depends on, for a given fluid, on its density. G is a constant, gravitational acceleration constant, and how high you go. So there's a linear increase in here. So let me in fact address this and derive this quantity. So in the static case, all forces must vanish here. So now if you take a little volume element, namely this here, this little element here, and ask yourself what forces are acting on that. So pressure is force perpendicular to that defining surface here. So here you have a little disk here. So here's the respective surface. Force is therefore pressure times that area. So now you have a component from the top, a component from the bottom, and the gravitational attraction of that little volume element with the liquid inside here. So let's formulate this now. The top pressure is minus P times A. The bottom is P plus dP times A. In the unit vector J direction is upward here, and the gravitational force is minus G, and a little mass element dm here. So let's take all of those forces now, insert it back into here. Then we therefore have minus PA here. And for the bottom part is now, let's multiply this out. P times A is PA, plus dP times A is dP times A. And then we have here minus G dm equals to 0. So therefore, minus PA and PA goes out. And what you have left then is dPA from here minus G times dm. Therefore, this is dP times A. And we can now replace the mass here, calculating this now using density. So the mass is there for the density times the respective volume, which is here A times dH here. So this little height here, dH times this area, that's the volume. Let's evaluate this now further. We can cancel out the area, so you're not depending on that specific area. And then have therefore dP, how the pressure changes per height, is therefore rho times G, and that is a constant. And therefore you can immediately conclude, since the slope here dP dH is a constant rho times G for a given liquid, you can integrate over this and therefore get P naught plus rho G times H. So let me therefore now come back. You should pause here now and actually write this up for yourself and think about that. Before I continue now on the slides, let me give you put some context into that. At what water depth is the pressure twice the atmosphere pressure? So let's take the atmosphere pressure as P naught here. how deep do you have to go below the water surface such that P after final pressure here is twice as large. So therefore you have 2 P naught equals to P naught plus rho GH, and let's solve therefore for H. Therefore you have then P naught over rho G, and let's take now the water density G and P naught the atmosphere pressure. If you plug this all in, you come to 10 meters. That means if you go 10 meters below the water surface, the pressure increases to twice the atmosphere pressure. Now, if you now ask the question, what is the pressure? How much does the pressure increase following for every 10 meters? So now, imagine you have a certain height, H1, and the respective pressure is therefore P1. And you go now to a different height, H2, and you have a different pressure. And what is now that pressure change if the change in height is just 10 meters? Well, that refers to 100 kilopascal. This is exactly numerically roughly the same value as one atmosphere pressure, in fact. So 100 K, so K is 10 to the 3, 10 to the 4, 10 to the 5, so it's about 10 to the 5 Pascal. It's exactly the same thing as here. And the depth at about 11 kilometers, so 11 times 10 to the 3, you would have a pressure of 111 megapascal. Mega is 10 to the 6, so this would be 10 to the 7, 10 to the 8, about 1 times 10 to the 8 Pascal. This is exactly what I showed you here before. Deepest ocean is about 1 times 10 to the 8 Pascal, just to give you a little bit of a feel for that. So please go through, derive this for yourself, take some notes, pause the video at this point, and go through these very simple illustrations here concerning the linear increase of pressure for a liquid. So now let me come back to the slides here and show you one beautiful example of a practical application using the fact that a liquid cannot be compressed. And that is used in, for example, in a hydraulic brake system. This is used, for example, in a hydraulic press here. Imagine you have a cylindrical system with a liquid inside. Typically it is an oil. And you have here a piston of a certain area, AIN, and you push here with a certain force over that area, giving rise to a certain pressure. That pressure is now identical on this side here. A liquid cannot be compressed. However, you have here now a larger area and can sustain therefore a larger force here, for example, to lift a car. Let me also show you this now as an example. So you have exactly this configuration here. So imagine you have here a car with a much larger diameter here compared to where you would crank with a hand crank as much smaller diameter and a much smaller area, and therefore a smaller force here. But again, the liquid cannot be compressed. So on both sides, this 0.1 here versus 0.2, the pressure is the same. P1 equals to P2 equals to P. So let me actually show you this now. Imagine the car has a mass m, therefore the respective gravitational force is m times g. That is now balanced by the pressure, the force onto the liquid here, but now spread over this area, giving rise to a pressure P. So force is pressure times the respective area, A2 here. So if you calculate this for a cylindrical diameter, so this would be here P times pi R2 squared. Imagine the radius here is simply R2 here. Now, that pressure here is, however, identical throughout this liquid here. So you can calculate that pressure here now as the ratio of that force F1 divided by that area, which would be now a different radius, namely R1, which is smaller than here. So F1 divided by pi R1 squared. So pi cancels out here. And therefore you have, let's go back to the very beginning, mg equals to F1 times the radius of these two cylindrical systems here squared, R2 divided by R1 squared. So now therefore F1, if you now solve this, is therefore mg from here times R1 divided by R2 squared. Now R1 is much smaller than R2 here. If we calculate this ratio here, this would be a 1/8. So therefore it is mg, which would be quite a lot for a car, divided by 64. So you apply a force of 64th of over mg. So that's the principle of a hydraulic lift here, in fact. And similar being used then for a brake system. So now how is actually pressure being measured here? A barometer measures the absolute pressure of a fluid, typically air. Although modern barometers often have electronic sensors, the principle of fluid pressure measurement is best illustrated by the traditional mercury barometer here. Namely the atmosphere pressure, which I've stated to you before. And you put in, imagine you would put mercury in here, which is a metal, which is liquid at room temperature. It would rise to a certain level here in this cylinder here, namely to a level of 760 millimeter. And that refers to that unit which I mentioned to you before. 760 torr refers to 1 atmosphere pressure. A manometer measures the pressure difference. Gauge pressure is a measure of the pressure relative to the ambient atmosphere. Let me see. I don't think there was another part in here. So we'll come back to some calculations a little bit later. Let me now state a very important principle, namely the so-called Archimedes principle. Namely, and that has to do if you now take an object of a certain volume and submerge it inside of a fluid. Fluid can be a gas or it can be a liquid. So Archimedes principle is not restricted to a liquid only. It can also be applied to a gas. When a fluid is in hydrostatic equilibrium, the force due to the pressure differences on an arbitrary volume of a fluid exactly balances the weight of the fluid. Now, replacing the fluid with an object of the same shape doesn't change the force due to the pressure difference. Therefore, the object experiences an upward force equal to the weight of the original fluid. And this is the so-called buoyancy force. And let me explain this to you in more detail here. So imagine you have a container with a certain liquid inside, and then you put in here an object, and that object has a certain volume. Before you place this object, looks like a pear-shaped inside of that liquid, that water level would be somewhat lower here. Now you place this object, it displaces a certain amount of volume here. And that object here experiences, in addition to its own gravitational force, an upward force, which is given by the gravitational attraction from the amount of liquid which is displaced by this object here. So it would be the mass of the liquid it displaces times g. But the mass is calculated now as the product of density of that liquid times what? Times the respective volume of that object here, because that's the amount of displaced liquid. So therefore the buoyancy force in magnitude is rho, the density of the liquid, times g times v, namely the volume of that shape that you displace. And there are very, very beautiful phenomena, therefore, for that, and I will go through some calculations, namely, for example, an ice mountain. If a submerged object, for example, is less than a fluid, then the buoyancy force is greater than its weight and the object rises. In a liquid, the object eventually reaches the surface. Then the object floats at a level such that the buoyancy force equals to its weight. That means the submerged portion displaces a weight of liquid equal to the weight of the object. in the atmosphere, so now if we're talking about a fluid, namely a gas, a buoyancy object rises to a level where its density is equal to that of the atmosphere. So you take advantage of a balloon, for example, a helium, not a helium balloon, for example. Let's not take hydrogen because that's quite dangerous, or hot air. The density there is much smaller than the surrounding air, and you displace that, giving rise to an upward force. And I will go through now through a calculation of the you applying this Archimedes principle now, for example, through an iceberg. So let's stop here, and let me first go through the basic application of the Archimedes principle. So imagine you have a person here standing underneath water here. You would actually, which is quite challenging, as you can see, you would float by itself. But let's ignore this for a moment. I'm talking up here about mainly about displacing submerging an object and the force that you still have to potentially apply. And there's a clear change in direction depending on the density of this object. Namely, if you hold a piece of iron in your hand, or if you're holding a piece of wood in your hand. So let's focus entirely on this object that you hold in your hand here. So what are the forces on this object? Well, number one, there's the gravitational force. Then this object with a certain volume V here displaces a certain amount of that liquid. So there's a buoyancy force, an upward force here. And then in addition to that, let's imagine it is a very heavy object, a metal, there would be an upward force here. And I give it a proper direction through this unit vector direction J upward here. The volume is defined as the mass over the density of this object. When all of this object is stationary, all of these forces have to add up to 0. So let's now formulate these three forces. The buoyancy force is now what? Well, it's the mass of water, namely the mass of the respective amount of water that you displace by this object of volume V times G. So therefore the mass of that is the density of water times the volume of this object times G. The applied force is simply formulating it as the applied force times J, the magnitude. That's what we want to calculate. And how the direction changes, if it were to be a piece of iron, then I would expect this force to be upward. I still have to apply an upward force. Or if it would be wood, then I have to actually apply a downward force. Otherwise, it would rise to ensure that it's stationary. Gravitational force is minus mg. And then I replace here m by the density of this object times v here. So note here we have two densities. The density of the liquid on the one hand, and the density of this object on the other hand. So let's insert all of these three components now into here. So what do we have now? We have rho, the density of water times the volume of this object times g, plus the applied force, minus rho, the density of the object, v times g. And then, as you can see here, let's replace now the volume by the ratio of m over rho. Rho cancels out here for the density of this material. And let's solve this now for the applied force. So therefore, let's bring these two terms here to the other side. So what do we have then? We have then therefore mg, which is here, and then this term will have a negative sign. So we also have mg here. You can take this out, but you have here a ratio of the density of water divided by the density of this object here. And let's calculate now. So imagine you would have this situation here in air. Then the density in air relative to the density, let's say, of a piece of wood or iron is essentially 0. So this would be 0. Then you would simply apply as the applied force simply mg to ensure that this object is actually not moving. But this changes now quite drastically. So let's take a liquid, a fixed liquid, namely water, but let's calculate now this part here for different types of material. So water is roughly 1 gram per cubic centimeter, but for iron this is quite a bit larger, 7 grams per cubic centimeter. So what do we therefore expect? If this ratio is much smaller than 1 here, namely the density is much larger than water here, then 1 minus a very small ratio here, much smaller than 1, would be smaller than 1 but close to 1. So in this case for iron is 0.86 here. And indeed the applied force would be smaller than if you would just do it outside in air. Let's change this now. Let's now take a material where the density is in fact smaller than for water. For example, wood is roughly 0.7 grams per cubic centimeter. Then what we therefore expect, this ratio would be therefore larger than 1. 1 minus something which is larger than 1 would be therefore a negative number. In this case we would get here minus 0.43. What does this minus sign now mean? Well, minus sign relative to the assumed direction of the applied force upward here, meaning we have to press down that piece of wood to completely submerge. And that is entirely consistent with our experience. Let me calculate now this scenario for a floating iceberg and really account for the fact that an iceberg, the largest fraction is actually underneath compared to the top part, which came, I believe it was in 1912 when the Titanic actually crashed against one of this iceberg in the Newfoundland area. So let's take the unit vector direction again here, upward here. Buoyancy force is upward here by the amount of water displaced by the frozen ice plus Fg here. So Fg is the mass of this ice times g. Mass I replace as the volume of the ice here, so the total volume times the density of ice. And then the buoyancy force is the mass of the water displaced by the submerged part here times g, so the density of water times that submerged fraction. What I want to calculate now is that fraction here, the volume, the submerged part over the total volume part. Well, in static equilibrium, these two forces add up to 0. So in magnitude, both of these forces have to be the same. So rho of ice times the volume of the ice times g has to be equals to rho of water times the volume of the submerged part times g. So if you now take the volume of the submerged part divided by the ice, that equals to the density of ice divided by the density of water. And if you now take exactly that, then what you will see that this ratio is roughly 0.86. So the submerged fraction, namely this part here, is 86% of the total. So 86% is below the actual surface. So a very large fraction. And that refers to this beautiful illustration, in fact, here of an ice mountain. There's a very large fraction below the water surface than compared to above. So please stop here and go through these two calculations of the apparent weight of an object underwater. Very much depends on the density of that object relative to the surrounding liquid. And then go through this simple calculation of a floating iceberg here. I have also included in here this very famous example of Archimedes, what he was actually supposed to do, namely to answer a question if a crown that he was given is in fact made out of gold. Please go through this example yourself. And read this up in your textbook. So here's in fact an example for a tire pressure. I told you before, in my car I typically put in it's an XC70, it's a T6, typically 36 psi. 4.7 psi is about 1 atmosphere pressure, so 36 psi would be roughly 2.5 atmosphere pressure. So that's a typical tire pressure. So that concludes that first part of the notes. So please go through this carefully. The derivation of the pressure as a function of height inside of a fluid, number one. Number two, various steps concerning how does the pressure change if you go below the water surface, and let's say you do this by 10 meters, that would increase the pressure by a factor 2. How much does the pressure change for given 10 meters? And then here's an example for the pressure at the lowest seabed on Earth, roughly at a depth of 11 kilometers. Here's a beautiful example of the fact that a liquid cannot be compressed, hydraulic lift, and then go through this calculation of an apparent weight underwater and the floating iceberg. The Archimedes idea, I leave it up to you to go through this yourself, review this in your textbook, and here's a simple tire pressure example. So let me now go back to the slides here and very briefly illustrate a couple of now phenomena when a fluid is in motion. So a moving fluid, be it a liquid or a gas. Moving fluids are characterized by their flow velocity as a function of position in time. So in a steady flow, what do we mean with that? The velocity at a given point is independent of time. Steady flow can be visualized by streamlines, which are everywhere tangent to the local flow direction here. In unsteady flow, the fluid velocity at a given point varies with time. So now in the so-called continuity equation expresses the conservation of mass in a moving fluid. And the continuity equation refers to the following, that the product of pressure times velocity times area is simply a constant. And imagine you now have a liquid, then pressure is anyway a given constant here. Therefore, namely in an incompressible fluid, for example, the liquid, the product of velocity times area is simply a constant. So what does this now give? Let me give you a very well-known example. Imagine you look at the flow of water in a river, and you're looking at the cross-section of that river. And one time that river is very wide. Okay, so the area is very, very large. V times A is a constant. Now the shape of that river all of a sudden changes after a few kilometers. It would be much, much narrower. So A would be much smaller. But still, you still have to transport the same amount of mass, conservation of mass. So therefore the product V times A has to be the same. So therefore in that section where the cross section of that river is much, much smaller, the velocity would be much larger. And this is precisely what you see when you're looking at a river which is very, very wide. Large cross-sectional area, the velocity is very small. Compared to when the river is very, very narrow, the fluid would move extremely rapidly. So here, for example, in this case here, the velocity here would be much, much larger compared to here. Before I come to the Bernoulli equation, let me in fact show you the derivation of this continuity equation. So basically what you consider a mass element at one location, so let's say here, and a mass element in a second location here. Let's formulate now the mass element. Density times volume is the mass, and the volume is simply A1 times a given length here of a little cylindrical element. I label this in the notes as L1, or here in the slides as delta X1. And you can replace the L1 that you consider this liquid or this fluid to flow. So therefore you consider this over a certain time interval delta T and calculate L1 as V1, the velocity of this fluid, times delta t. Now you do the same thing at location 2 here. And then you set these two equals to each other. And then what you're finding here, you can cancel out delta t, that the product of density times area times volume has to be the same. And if the density is now the same, then you come to so I apologize, this I refer to here this as pressure. This is in fact of course the density here. This is not the pressure here, so this simply is in fact the density, not the pressure here. So if for a liquid, for example, the density is a constant, then the product of A times V is a constant. An application is the flow in pipes with different diameters. It would, if the area is very large, the velocity is small, and the other way around. So now let me show you now an extension of that. So the extension is now concerns the Bernoulli equation. And let me first read the Bernoulli equation, in fact. And let me first illustrate this here on this pipe section. So you have here a fluid flowing through this pipe section. That could be that could be a liquid, this could be a gas. In a section of the pipe with an area A1, which you show here at a height Y1, and then a section here with an area A2 at a height Y2 here. You in this see here the direction of the velocity V1 from left to right, and here the direction of velocity V2 also here from left to right. Imagine it's a liquid here. Then the Bernoulli equation states the following, that the sum of the pressure, for example the pressure here in this pipe section, plus half times the density times V squared, namely the velocity, plus the density times G times H, so in H referring here to that vertical location Y1, Y2 here is a constant. Okay, from that you can see immediately already, if that is to be a constant, if you change one of these quantities, then that goes at the expense of changing the other quantity here, for example. So let me give you a little bit of an idea of how to derive that. It's actually not very complicated, and this is in fact a nice exercise using the energy methods that you have in fact learned so far. So let's see. I'm not writing this out. This is not very complicated. Let's go here after the continuity equation to a Bernoulli's equation. So the kinetic energy theorem states that delta K, the change in kinetic energy, equals to the amount of work done. So K final minus K initial equals to a half delta M V2 square minus V1 square. Now V2 and V1, these indices V1 and V2 refer to this location 2 here at height Y2, and 1 referring to this location 1 here at height Y1. So at 1 versus 2 here now, the work equals to minus the change in the negative, the change in potential energy, plus the amount of net work potentially performed here. So concerning now the change in potential energy due to gravitation, you can easily write this down. This is mass times g times height, so delta mg times y2 minus delta mg times y1. What does delta m refer to? Well, it's the mass in this little tube section here over a time interval delta t. So how much liquid flows in a time interval delta t, just like what we did before for the continuity equation. So let's evaluate now at point 1 and point 2 separately the work performed by displacing that liquid element. So meaning that liquid which moves along at a certain time interval delta t under a certain amount of pressure. The pressure is of course force divided by area, so the force by itself is pressure times area. And that's what you precisely see here. So now force times displacement. These are two vectors which are parallel, so therefore you simply have here F1 times delta x1, the force is a constant. F1 can be replaced by P1 times A1, And delta x1 is the distance over which this liquid flows. So we can simply write this as v1 times delta t. So now you pull out p1 here, and then what do we have here? We have therefore now the density formulated in here, multiplying this whole these three terms here, a1, v1, delta t by the density. Then we have to also divide it divide again by the density. So we're multiplying, so to say, this expression by the density divided by the density. Okay, that will become clear why we do that. So the density is therefore written here times a quantity which is volume here, a1 times v1 times delta t. This is delta x1, or labeled in the other in the slide delta L1. This is therefore a volume, and density times volume is the mass. So therefore what we have here is P1 times delta M divided by the density. So it's simply to rewrite this. That's why we multiply this and divide it by density. You can do exactly the same thing for point 2 here. And then you get P2, the pressure at point P2, times delta M over the density. And the net work performed is therefore the difference, W1 minus W2. So therefore you see here pressure difference. Let's insert this now back into here. And then we invoke the fact that delta K equals to a half delta M V2 squared minus V1 squared. This is here the left-hand side. Delta U, the change in potential energy due to the gravitational force, has been written here. And the net work performed due to the pressure difference we just calculated before here. So let's insert this all back into here. So then we have delta K, the difference in kinetic energy, equals to minus delta U, the change in potential energy due to gravitation, and the net work performed by the pressure difference, which you see here, the last two terms here. And then I leave this up to you to rearrange this. You can cancel out delta M here, and then you come to the Bernoulli equation, that P1 plus a half rho V1 squared plus rho times G Y1 equals to the respective sum of the respective terms at point 2. And therefore, the sum of these three quantities has to be the same. So that's the Bernoulli equation. So what does this now imply? This implies, once again, if you change one of these quantities, it goes at the expense of another quantity. And let me give you now a beautiful application of that. I strongly encourage you to separately download the notes and click on this link here. And there's a beautiful demonstration, namely of a Bernoulli principle, namely of an airplane wing. And what this guy shows you here is he's blowing on that airplane on the top with a larger velocity. So larger velocity on the top, smaller velocity on the bottom here. So larger velocity on the top, smaller velocity on the bottom here. The pressure difference between on the paper is roughly, the potential is roughly the same. So forget that term here. So therefore this gives rise to a pressure difference. Namely, the pressure on the top is smaller than the pressure on the bottom here. Pressure on the top is smaller, pressure on the bottom is larger. Pressure is force divided by area. So therefore this gives you an upward lift, force, pressure times area upward. And this is exactly what you see here. Blowing on the top gives you an upward lift. So now let's come back to the airplane. So that is in fact a photograph which I took out of the window on my way back from China to the United States last week. Air flows faster on the top of the wing than on the bottom of the wing, the way the wing is shaped, and therefore you get an upward lift. If you now want to go down, you change through these elements here in the back of the wing exactly that. You alter the way the speed of the air flows on top of the wing here relative to the bottom of the wing. There are some further applications here. I'll leave this up to you here. And I want to show you one last thing here, namely the so-called Magnus effect, where again, due to with the Bernoulli equation, so I have to stop here right now.